An avid cyclist dreams of turning his passion into a business. He consults his banker to help find the best path. Now bike wheels are being built, and all it took was a little push to get rolling. First Horizon Bank. Let's find a way. Go to firsthorizon.com/Clint. This morning in the Atlanta airport, no one's missing a meal on Mac Wilburn's watch. With 11 restaurants to serve passengers, he's got dining for every destination. And it all started when Mac talked with First Horizon Bank about opening a franchise in the airport. Now it's open for business and cleared for takeoff. First Horizon Bank. Let's find a way. Go to firsthorizon.com/Mac. First Horizon Bank, member FDIC.
Welcome back to Astronomy Daily. This is little brother Steve Dunkley sitting in for big brother Andrew Dunkley, who is, of course, away on a well-earned holiday.
Astronomy Daily, the podcast, with your guest host, Steve Dunkley.
Now, I hate to say it, but my skies are full of rain at the moment. It's been a drizzly, miserable day out there on the east coast of Australia. I hope it's a better day where you are, wherever you are in the our corner of the world. And I just want to send out a happier note to some of the people who've been very encouraging to me online. A very big hello to Sandy Fern, Rebecca Seaton, Paul Keane, John Carl, of course, and my good friend Paul Searles, most of whom are hailing from Australia, which of course is the most wonderful place in the universe. Thank you for your encouraging comments. I really do appreciate it. And joining me, of course, is our sidekick and intrepid AI reporter, Halley. Welcome aboard again, Halley.
Rain, go away. Come again another day.
Yes, that's how it goes, and that's how we feel, Halley.
But why would you want the rain back again?
Oh, well, the rain is useful, but not when it comes down in such great amounts. And the east coast of Australia is getting hammered pretty badly, especially in the northern New South Wales to the Queensland border and, in the Lismore districts of New South Wales and around there. And even as far down as Melbourne in Victoria, there's a lot of rain around at the moment. And unfortunately, a lot of flooding.
Oh dear, I hope things get better soon.
Well, thank you, Halley. I know we're all hoping and praying for clear skies. Why don't we kick off with a little bit of news and get started with our episode?
Okay then, great idea. Astrophysicists have performed a powerful new analysis that places the most precise limits yet on the composition and evolution of the universe. With this analysis, dubbed Pantheon Plus, cosmologists find themselves at a crossroads. By putting prevailing modern cosmological theories, known as the Standard Model of Cosmology, on even firmer footing, Pantheon Plus further closes the door on alternative frameworks accounting for dark energy and dark matter. Both are bedrocks of the Standard Model of Cosmology but have yet to be directly detected and rank among the model's biggest mysteries. Using various spacecraft and ground-based telescopes, astronomers have conducted multi-wavelength observations of a Type 2N supernova known as SN 2017 HCC. Results of the observational campaign published recently shed more light on the properties of this supernova. The study found that late-time infrared emission dominates the spectral energy distribution of SN 2017 HCC. It turned out that although this supernova had a very high bolometric luminosity likely to be due to circumstellar interaction, it was faint in X-rays and radio wavelengths. Supernovae are powerful and luminous stellar explosions. They are important for the scientific community as they offer essential clues into the evolution of stars and galaxies. In general, supernovae are divided into two groups based on their atomic spectra. Type 1 supernovae lack hydrogen in their spectra, while those of Type 2 showcase spectral lines of hydrogen. When it comes to Type 2N supernovae, they showcase narrow optical emission lines and hot continua. These supernovae are usually observed when they interact with dense material surrounding the star, hence the light seen here on Earth comes mostly from such interactions. While astronomers have seen the debris from scores of exploded stars in the Milky Way and nearby galaxies, it is often difficult to determine the timeline of the star's demise. By studying the spectacular remains of a supernova in a neighboring galaxy using a team of astronomers has found enough clues to help wind back the clock. The supernova remnant called SNR 0519 is the debris from an explosion of a white dwarf star. After reaching a critical mass, either by pulling matter from a companion star or merging with another white dwarf, the star underwent a thermonuclear explosion and was destroyed. Scientists use this type of supernova, called a Type 1a, for a wide range of scientific studies ranging from studies of thermonuclear explosions to measuring distances to galaxies, across billions of light-years. SNR 0519 is located in the Large Magellanic Cloud, a small galaxy 160,000 light-years from Earth. Astronomers combined the data from Chandra and Hubble with data from NASA's retired Spitzer Space Telescope to determine how long ago the star in SNR 0519 exploded and learn about the environment the supernova occurred in. This data provides scientists a chance to rewind the movie of the stellar evolution that has played out since and figure out when it got started. Pictures of the sky can show us cosmic wonders, movies can bring them to life. Movies from NASA's NEOWISE Space Telescope are revealing motion and change across the sky. Every 6 months, NASA's Near-Earth Object Wide Field Infrared Survey Explorer, or NEOWISE spacecraft, completes one trip halfway around the Sun, taking images in all directions. Stitched together, those images form an all-sky map showing the location and brightness of hundreds of millions of objects. Using 18 all-sky maps produced by the spacecraft, with the 19th and 20th to be released in March 2023, scientists have created what is essentially a time-lapse movie of the sky, revealing changes that span a decade. And that's the news. I guess a photo of your sky wouldn't be very nice about now, Steve.
Oh, I'm afraid you're so right there. It'd just be grey and wet.
Have a nice hot chocolate, that'll do the trick.
Oh, I think you're onto something there. Okay. Now, you remember Cassini, don't you? The mission to Saturn a few years back. Researchers have been busy combing through the ocean of data that little probe sent back, and they're finding out big things about tiny particles. Southwest Research Institute scientists have compiled 41 solar occultation observations of Saturn's rings from the Cassini mission. The recently published compilation will inform future investigations of the particle size distribution and composition of Saturn's rings, key elements to understanding their formation and evolution. For nearly 2 decades, Cassini's NASA spacecraft shared the wonders of Saturn and its family of icy moons and signature rings, but we still don't know definitely the origins of the ring system, said Dr. Stephanie Jarmak, a researcher in the SWRI Space Science Division. Evidence indicates that the rings are relatively young and could have formed from the destruction of an icy satellite or a comet. However, to support any of the one origin theory, we need to have good idea of the size of the particles making up the rings. Fair enough. Cassini's ultraviolet imaging spectrograph, UVIS, was uniquely sensitive to some of the smallest ring particles, particularly with the observations it made in the extreme ultraviolet wavelength. To determine the size of the ring particles, UVIS observed them when the instrument was pointed at the Sun, looking through the rings in what's known as a solar occultation. Ring particles partially blocked out the path of light, providing a direct measurement of the optical depth, a key parameter for determining the size and composition of the ring particles. The compilation published in Icarus Journal also delves into the variations in the optical depth of occultation observations, which can help determine particle size and composition. During an occultation, light emitted by a background source, such as the Sun, is absorbed and scattered by the particles in the light's path. The amount of the light blocked by the ring's particle provides a direct measurement of the ring's optical depth. Including optical depth is a vital understanding to the structure of the rings. Ring systems around giant planets also provides test beds for investigating fundamental physical properties and processes in our solar system in general, Jarmak said. These particles are thought to result from objects colliding and forming in a disk and building up larger particles. Understanding how they form these ring systems could help us understand how planets form as well. And seeing the incredible diversity and variety of planets and moons in our neighbourhood, I reckon that'll keep our scientists busy for eons.
You're listening to Astronomy Daily podcast.
Recently, our client Tommy met his banker to discuss continuing his father's restaurant legacy. In us, he found a partner that understood the importance of passing the torch. First Horizon Bank. Let's find a way. Go to firsthorizon.com/Tommy.
And while the rain is coming down outside, there's potentially more coming down outside than just water. More than 60% of the launches in 2020 resulted in one or more rocket parts making an uncontrolled re-entry into the atmosphere. That sounds pretty bad. While no one was hurt or has been hurt so far by that debris, thankfully, with the numbers of rocket launches over the coming decade on the rise, the chances of casualties are presumably increasing. A new study describes how current methods of assessing risk just aren't up to the task and how new steps need to be taken. Rocketry is a complex business. A typical launch will require multiple stages to get a payload into orbit. Usually, everything goes well, with the individual stages designed to either burn up in the atmosphere or end up on an escape trajectory away from Earth. But just in 2020, as I mentioned, 60% of the launches to low Earth orbit ended up with at least one significant rocket part abandoned in an uncontrolled orbit. These pieces of space junk are no longer under any human control, and they will eventually fall back to Earth. Not good. When they do, they will first enter through our atmosphere. While the heat of that re-entry is good at vaporizing most materials, experts estimate that for any one piece of rocket, about 20 to 40% of its mass will make it to the Earth's surface. Obviously, this is a significant risk to lives and property. And while to date there have not been any serious consequences of uncontrolled rocket debris, we cannot continue to assume that this is going to be true into the future. Many companies are planning on launching fleets of communication satellites, and this means more rockets and potentially more space junk heading home randomly. Some space agencies like NASA require that any launches have no more than 1 in 10,000 risk of harming people or property from uncontrolled debris re-entering the atmosphere after the launch. Several astronomers have pointed out that this is an inadequate figure. Many companies are given waivers to avoid having to satisfy this rule if it's too expensive to uphold it, and this ratio may be fine for a limited number of launches every year, but it ignores the cumulative effect of thousands of launches happening year after year after year. Researchers analysed the current orbits of 600 known pieces of space junk and estimated where they will re-enter the Earth atmosphere, discovering that most pieces of uncontrolled space junk were associated with geostationary orbits, which means that the risk of re-entry is concentrated near the equator. That's not so good for people living near the equator. But the countries that typically make these launches are situated away from the equator, so they are in effect shifting the risk of debris from their own populations into countries that didn't even participate in the launch process. Overall, the researchers found a roughly 10 to 20% risk of casualty over the coming decade from uncontrolled debris. That casualty could take the form of a single person getting hit, or it could be something more catastrophic like a large building or an aeroplane even. Now they're calling for more honest and consistent risk assessments and more uniform application of the rules by the community to properly address the next generation of spaceflight. And there we have it. That's another episode of Astronomy Daily. Thank you for joining us. And remember, you can catch all the episodes of Space Nuts with Andrew Dunkley and Professor Fred Watson, as well as the free podcast Astronomy Daily at this address, spacenuts.io. Go over there and click the links and you can enjoy all of the episodes past. As we post them, you can have them. I'm Steve Dunkley, sitting in for Big Bro Andrew Dunkley while he's on break. Thank you, Halley, for all your help today and the words of encouragement as well.
Wishing everyone in Australia some better weather, guys. See you all next time.
All the best, everybody. See you next time.
Astronomy Daily, the podcast, with your guest host, Steve Dunkley.